Moving on then to deriving the equations further, we said following a particle. So let's think of this particle or a fluid parcel. That's the terminology we used before when we talked about adiabatic motion of a parcel in the atmosphere and so on. Just for simplicity, imagine that it's a cube with face delta x. Let's say this is delta x, going into the page here is delta y, and in the vertical direction is delta z. We will see when we go on the sphere that we typically use x as the longitudinal direction, y as the latitudinal direction, and z as the local vertical. The assumption we always make that the atmosphere and ocean are thin shells on this big sphere allows us to basically use a local Cartesian coordinate. But nonetheless, coming back to this, what is the area and various forces acting on this? Let's start with pressure, right? Any water parcel or air parcel is going to feel pressure from all sides. So just make sure you understand the corners. We are here. The center of this cube is going to be x, y, z. So we move in half delta x in the x direction on either side, half delta y, and half a delta z. So if you go to this corner, you're going from the center by minus half delta x, minus half a delta y, and plus half a delta z. Okay? So because you're going back in y, back in x, and up from the center by half a delta z. So similarly, the other corner is x minus half delta x, y plus half delta y, and z minus half delta z, and so on. So you can just make sure that you understand each of the corner coordinates just to get oriented on how we will write these equations. So let's look at the face B here of this parcel. What is the pressure? First of all, it's compressing. Pressure always does this, right? So on B, it's pointing towards the minus x direction, so it is minus p at x plus delta x over 2 because we are moving in the x direction from the center, and we are in the center of this face, so we are at y and z. So the average pressure acting on this face B is acting at x plus half a delta, and it's acting in the minus x direction, so that just gives you pressure force at face B. Similarly, you can write pressure force at face A, and then take the difference for the net pressure force in the x direction. Okay, so how do we write F equal ma in this case? Clearly, it's just rho times delta x, delta y, delta z, where rho is the density. Delta x, delta y, delta z gives us the volume of this cube, the parcel that we are looking at. Du dt is the acceleration, should be equal to the net force F. That's our F equals ma for this parcel, right? Writing out our du dt as du dt plus u du dx, v du dy, and w du dz. So it's the advection of u, momentum in the x direction, by the flow field. Local change in time and advection in x, y, and w. Note here, du dx, du dy, du dz carried by u itself, v, and w. This is what makes these things non-linear, right? U advecting its own variations. Okay, so you can write this as du dt plus u dot grad u, where grad u is the gradient, and you're dotting it with u. Okay, very straightforward. And we will expand on that in the next podcast, but make sure you understood how we do the parcel, its corners. We are looking for force balance at its center, so we have to look at every force on every face, and right, x direction, y, x direction, y direction, z direction, and the forces are acting on the faces of this little cube. It's arbitrarily small, so you have to think of it as a particle following as a little cube. We're following this particle, which is represented as a little cube. These are very simple, but you must go through them to make sure that you really understand what is being said.